Hello everyone! In this video I am going to compare sorting algorithms. These algorithms are Insertion Sort, Bubble Sort, Heap Sort and Quick Sort. I prepared as an example solution in Visual Studio 2019, which consists of implementation of mentioned four algorithms. The solution is a C++ console application. Let's take a closer look at implemented algorithms. First algorithm is Insertion Sort. We can see at the picture that there are 8 numbers to be sorted. Firstly, number 4 is sorted. We move to second number, which is 3, and we move it just before 4. Then we take third element, which is 2, and move it before 3, since 2 is less than 3. The next number is 10, and we do nothing here because sub-array consisting of first 4 elements is sorted. For the following number 12, we also do nothing. Next element 1 we insert just before 2, then we have 5 which we insert before 10 and after 4. Finally, last element 6 we insert before 10 and after 5. This sorting technique is similar to sorting cards from the deck. Let's see implementation of this algorithm. At each iteration we pick next element which is pointed by I indexed. Then we move all previous elements one place right until the I element is less than J element, and finally insert I element at the correct place. Let's take a look at the second algorithm, which is Bubble Sort. In first pass we swap 7 with 6 because 7 is greater than 6, then we swap 7 with 4 and finally 7 with 3. After first pass we have greatest element at the end of an array. In second pass we swap 6 with 4, then 6 with 3. We now have second largest element at 1 before last place. In third pass we swap 4 and 3, so after that we have sorted array. At each pass the largest element of subarray bubbles to the end of subarray. Let's look at the code. We iterate from I equals to 0 to I equals to vector size -1. Loop invariant is that last I elements are sorted and in place. If J element is greater than J plus 1 element, we swap them. Let's look at the next algorithm, which is Heap Sort. It operates on a data structure called max heap. Max heap is a binary tree which satisfies the following property. Value in any tree node is greater than the values in each child. In current screen we see that in the root there is 50, its left child is 10 and right child 23, which are less than 50. The same way children of 10 node are also smaller than 10, and finally child of 23 node is -4, which is smaller than 23. Heap sort algorithm makes max heap and then swap root element, which is 50, with the last leaf, which is -4. Then heapify procedure is called, which restores max heap by swapping -4 with the largest from its children, which are 10 and 23, so 23 swaps with -4. Then again we swap 23 with the root with rightmost leaf, which is 7, and again we call the procedure heapify, which swaps element 7 and 10 with which preserves max heap property. We continue until only the root remains. At that point we have array sorted. Let's look at the code. We've got parent, left and right functions that returns the corresponding indices. Then we have heapify procedure, which swaps largest of a node children if it's greater than the number in the node all the way up to the leaf. It is recursive procedure which calls heapify on its children that was swapped. Then we have build heap procedure, which builds max heap from the vector of ints by calling heapify on first non-leaf node up to the when I equals 0, which is the root. Finally, we have heap sort algorithm, which consists of build max heap, call and then swapping the root vector to sort from 0 with the rightmost leaf, which is vector to sort from I, decrementing heap size by 1 and call heapify on the root. The last algorithm is quicksort. At the current photo we have array of 7 elements. We then partition it around the last element, which is 70. In the left subarray we have elements less than 70, and in the right subarray elements greater than 70. Then we swap pivot element, which is 70, with leftmost element in the right subarray and recursively call quicksort on the left and right subarrays. So we again partition around 50 elements and right subarray around 80 elements. We continue doing that until we have subarrays of 1 element. Let's look at the partition function. In our partition example we have array of 7 numbers. Pivot element is 70, low is 0 and high is 6. We traverse elements from j equal low to high minus 1, array 0, 10 is less than 70, so we increment I and swap array 0 with array 0, so do nothing because it's the same element. Then we increment j by 1, its element is greater than pivot, so we do nothing. Then we increment j by 1, which is now 2. Second element of array is 30, which is less than 70, so we increment I and swap array 2 with array 1, so 80 with 30. And we repeat the same procedure until we traverse with j index to the end of an array. The invariant here is that I plus 1 points to the beginning of subarray with elements greater than the pivot element. Let's see the code. If left index is less than right index, we do the partition and then call recursively 2 times quicksort on 2 subarrays created by partition. Now let's take a look at main function. We create vector of 10,000 integers, then initialize random number generator by calling srand with parameter time null, then assigned each element of vector a random integer. Then we create second vector, which is equal to input vector, and we also create time point now and assign it to start to variable. Next, we call quicksort on vector 2, and after that we save current time point to variable end2. The time that our quicksort took to complete is the difference between end2 and start2. So we save it to div2 variable, and then we save it to s2 variable. We repeat the same procedure for heap sort, bubble sort, and insertion sort. At the end, we output to console running times of 4 algorithms. Let's run our program. We see that heap sort and quicksort have similar running times, which is less than insertion sort. The longest time has bubble sort. It confirms that quicksort and heap sort have average asymptotic time equals to O from n times logarithm n, while bubble sort and insertion sort have time n squared. Let's increase vector size to 50,000 and see what happens. Now we can see that quicksort is slightly faster than heap sort, and bubble sort is 10 times more slower than insertion sort, which is greater 100 times than quicksort and heap sort. Now let's limit the range random numbers are generated to 100. Heap sort is now the quickest, which is 3 times faster than quicksort, and insertion sort, then it's insertion sort, and the slowest one is bubble sort. That's all. Thank you for watching.